from wireless interface as well. And if you're connected via GPRS, it means that you're not going to patch your kernel every year. The gateway, if it's going to stay there 5 years, it will have the same software there. No one's going to update it, patch it over GPRS. So, a bit of attacks. Let's start with code analysis. I said that Xmesh is sort of commercial extension of TinyOS. What it means is that there is part of code that you get only as compiled library. So you have to disassemble it and look at it in the code. There's about 15,000 assembler lines, so not that many. But you can use that, and you can use TinyOS. The code is very similar, so you can use variable names from TinyOS, and you get something like this, so something quite readable if you're really patient and you want to demonstrate something. To show particular examples, very important part of wireless networks is routing. So in TinyOS, routing is based on 2 metrics. It's link cost, so the cost of transferring message between 2 modes, and road cost transferring message between a mode and a gateway, which is sum of all link costs between the mode and the, let's say, internet. How to do it? All you need is basically a message counter that is inside each of the message you transmit wirelessly. And basically, according to the message counter, you just count how many messages you missed and how many messages you received. It's getting a bit messy with Xmesh because they just somehow decided they don't need counters in some messages, so data messages don't have counters, but well, yeah, whatever. So you can look into the code and you'll find out that when you update counters, meaning the number of missed and received messages here, you first count delta, so difference between the last sequence number you received and the actual sequence number, -1. And then somehow Xmesh did, or Crossbow did this, added extra 2 lines saying that let's decrease delta by extra 1. What it means is that if you skip one message, if you miss one message, so it means if you're missing every second message, it means 50% quality of link, that it will be still 100% quality for Xmesh. And you also can see that if the difference is, it means that the received sequence number is lower than the last one you received. So sort of now the counter is decreasing for some reason. So if it is not more than 20, the difference, nothing will happen. If it's more than 20, you will forget the mode and reinitialize its table. There is some sort of routing table, so you got records for all your neighbors. Just for good measure, Xcommand feature, extra feature for Xmesh. It allows you to send direct commands from the gateway to all the modes or selected modes. No routing, only broadcast, so brute force, no optimization for power. What helps to stop rebroadcasting? Each message got message ID, and each mode keeps internal counter. All fine. So if the internal counter is larger than received message, then the message is not processed because it's sort of repetition of something that I've heard before. The problem is that the internal modes counter is not the last seen message ID, but basically a number of processed commands. So if I've seen 10 messages, and now I get message with ID 40,000, I will keep rebroadcasting and receiving messages until I do it 40,000 times. Quite handy. We were just a bit surprised why we see so many messages now for no apparent reason in the network. A bit more worried about batteries as well. So attacks. When you think about attacks, you always have to think about hardware constraints. It's about counters, size of tables, and possibly crypto information you want to add to messages. So all data structures are size limited. Not always necessarily, but that's the way. So the most interesting part is jamming, I believe. You can jam, it's wireless, no problem. The question is, can the power used by the attacker be equal to what was wasted by victim, or lower, or even much lower? Or can we even use it for some sort of smart attacks? So we did a bit of experiments with jamming using one of the modes as jammer. So the power we used was basically equal to the power used by the victim. And the numbers here is basically percentage of successfully jammed messages. So it's very close to 100% all the time, but there are some spots for no apparent reason. Engineers didn't tell us, and yeah. But it happens. The distance between receiver-transceiver was 8 meters, and the position is position of the jammer. So even jammer that was very far, far away was still very successful. So selective jamming, can we do jamming when we select which messages we want to jam and which we just let pass? And we want to do it simply and with, let's say, effective implementation. So what we did was we compiled criterion into the mode's code, we uploaded the code, and deployed the mode and let it listen. The problem is that 802.15.4 radio chips work with blocks, the whole frames. So the chip receives the whole frame, processes it, and then says microcontroller, right, you can read out the block, the frame, and vice versa. Send me the whole block, the whole frame you want to send, and I will do it for you. But fortunately, all modes got debug mode. When you switch it to debug mode, what happens is that those are 2 pins from the radio chip. So when it starts receiving message, you suddenly see clock, and you see the data bits. Right, the documentation is not precise, you have to play with it a bit, but yes, you can bit by bit read out the message and just stop wherever you want. So that's what we did. When we read out, let's say, 10 bytes of the message, we processed it. Does it meet the criteria we've got? If yes, we started jamming, which took about 2 bytes to switch the radio from receiving to transmitting, and that was it. The final code quite small, about 100 lines in Nessie, which is C macro language. And yeah, jamming was just transmitting something random on the same channel. So we tried to jam node 24, which is down there. It was originally star topology. It sort of started behaving differently, but then stabilized into a star. When we stopped jamming, the mode 24 connected back. Protection, yes, there is some, but not very good, and it costs you energy or reliability of connections. What you can do is you can start manipulate routing tables. As I said, the whole routing is based on quality of links. You compute half of the information, the other half you get from the neighbors. So if you can fake messages from the neighbors, you can change the content of the routing table, or you can even send the whole content of routing tables into the mode. What you can do is to create steep deprivation attack by creating a loop between 2 modes. And what happens is that when one mode sends out a message, it will be kept sending between those modes indefinitely, basically. The duty cycle can be increased from well below 1% up to 10 or 20%. So very quick use depletion of battery. I saw that you have to think about, I said you have to think about size. So one of the problems is counters. You need them all the time. So there is one counter here, 8 bits. There is another counter here, 2 bytes, 16 bits. Another one here for crypto, 2 bytes. So it's not much. 2 power 16, 64,000 messages. It's still doable. You can try to do something. So what you want to do is, well, messages are rejected if the message counter is lower or smaller than expected value. But if it's larger by whatever value, then it's fine. There are several ways how to do it. You can inject fake messages, so the victim will forward back, so it will increase the counter. You can create a routing loop, as I said, and you can jam acknowledge frames, which will force the sending mode to replay frames several times. Or you can combine all of them. Try it, worked. Or you can think that size is everything, so the routing table size is 16. If the mode's got more than 16 neighbors, he has to forget some of them. So if you add another 16 neighbors, you basically can start sending whatever messages you want. Very briefly about traffic analysis. So this is the Anchorage room of Humber Bridge in Northern England. This is the network we deployed. Quite simple. The problem is that after 24 hours, when we looked at the topology that was during the time, you get almost complete graph. So again, if your listening is dropping on messages, then you can basically replay messages between any pair of modes, almost. What we can play with traffic, it's about topology. We can discover topology, find the most vulnerable place in the network. We can find routes to the gateway, or we can try to get data. Topology, you will use data that will never be encrypted because it has to be decrypted for the network to work. Partially encrypted data for routes to gateway discovery. Last few slides. There is TinySec, which is cryptographic library. It's quite cool. The problem is that it's only for Mica 2 modes, not ZigBee modes. So if you want to use it and do any experiments, you have to port it, which we did. There is radio, chip, then there is some sort of software for transmitting and receiving data. There is TinySec, again, back to the sort of communication library and then internal processing. The problem is that here, Mica 2, the old modes, use 1 byte at a time, while Mica Z will use the whole frame. So we have to create some sort of extra layer that will cover this problem. Which was surprising because we thought, well, people are still using this sort of stuff. And on the internet we found, yeah, we've got Mica Z, we just switched on in the Makefile crypto on, and we've got TinySec. But that's only what they thought. In fact, they had no TinySec available, and they were just communicating unencrypted, in an unencrypted way. With crypto, you got 3 types of problem: implementation, computational limits, and usage errors. Problems here, which is CBC MAC, if you know, it computes messages by 8 bytes. The problem is that it starts with 0, it increments position here, but checks for 7. So the MAC is computed from 7 bytes long blocks, not 8 bytes. So it's at least incompatibility, but yeah. Fortunately, it doesn't decrease cryptographic level because they use only 4 bytes from the MAC value, so it's still fine. Hardware limits, I don't think there are any. You can use increment asymmetric crypto. You don't need it that many times. You just need to create sort of trust between 2 modes at the beginning, then establish symmetric keys. And symmetric ciphers are very efficient today. Yeah. So TinySec is excellent because it's transparent for gateway. Gateway doesn't see whether TinySec is on and off. Why? Because it works only over a wireless interface, over the air. The RS234 connector transmits everything unencrypted. So what can happen when you are able to connect to one of the modes of the network that is using TinySec, you can send messages to the mode via RS234, 232, and the mode will just send it on your behalf encrypted. You don't need to extract any keys. You don't need to mess up with the code. It will basically work as sort of oracle and will encrypt, decrypt all the traffic. So for the end, we talked to Crossbow, which is